So it's time to start the last seminar of 2023. So it is, well, it's one is an old friend, I could say. So we've been know each other for quite a while. So Juan did his PhD at the University of the Balearic Islands in Palma de Mallorca, and afterwards continued to do a postdoc at Georgia Tech in Atlanta. Afterwards, he continued to another postdoc at Monash University in Melbourne, and then to Hong Kong before coming back to Europe. And currently, he has a Marie Curie fellowship at the University of Santiago de Compostela. And well, I mean, you best to tell us what you're gonna be introduced about. So take it away. Thank you.
Thank you, Alex, for the introduction, and thank you for the very nice invitation to talk here and come back to Lisbon 4 years after the last black hole workshop that I attended here. Alex was saying that he will be an expert on whatever he says here, but well, it's funny because I'm not an expert at all in numerical relativity, and I'm definitely not an expert in boson-stars. What I do is data analysis, so I'm telling you how we are using numerical relativity simulations to try to compare LIGO-Virgo data to collisions from boson-star mergers and see whether this could be in the data or not. If you're interested about this work, which I do in collaboration with people in Apero, so the group of Carlos Cardero, and people in Valencia, and mainly with Nico Sanchez, who was postdoc here a few years ago, then these are some references if you want to have a look. So this is a little summary of the talk. It looks a little bit little, but it's quite long. So it's a bit ambitious, but let's see if I have time to cover all of this. So first of all, I want to focus on gravitational waves or on compact mergers, very particularly in high mass mergers. And it's because these, what I call high mass mergers from 100 solar masses onwards, these are very, very tough to detect and interpret. But if you manage to do so, then the scientific outcome you have I think it is really good and it's really appealing. So this is why I basically care about this. Then in order to compare these high mass merger signals to numerical relativity, I'm going to describe a formalism we designed this year, which is based on comparing not the strain arising from the numerical relativity templates, but the Neumann-Penrose scalar to gravitational wave astronomy. And I will highlight why this is good. And it's basically because you eliminate lots of systematic errors arising from the extraction of the strain, as many of you surely know. And then as an application of this, we're doing 2 or 3 things with this kind of framework. But the main one I'm going to be dealing with or describing is that of searching for mergers of a particular type of boson-star, which are procastars, in LIGO-Virgo data. I'll explain why procas and not any other type of boson-star. And then I'll show the example of the gravitational-wave 1905-21 interpreted as one of these mergers, further events to 1905-21. And then I will describe something I've been working with Nico from Valencia, which is trying to include in our simulation some effects of quantum nature that may have an impact, or that actually have an impact in the gravitational wave emission, and trying to test whether this helps to fit LIGO data or not. So with that summary, let's start. The main problem I will be describing or I'll be dealing with is the following. We have some gravitational wave data, not always as beautiful and clean as this. And we will be making the assumption that this comes from some kind of astrophysical source, in particular, a couple of black holes or a couple of compact objects. And we want to figure out what the hell these are. What are the parameters and what's the nature of the object even? So the way we do that is by comparing with zillions of templates that we can generate for different types of sources. And then we end up constructing what we call probability distributions on the possible source parameters. So that's the basics of it. But we can do something on top. I mean, we don't only need, or we cannot only compare to one given model, for instance, for black hole mergers. We can have at hand 2 models. It can be for 2 different families of black hole mergers, namely circular and eccentric, or for 2 types of sources of different nature, as in this case will be, or at the end of the talk will be, black hole mergers and what I said, procastar mergers. So in this case, on top of estimating parameters, we can do what we call model selection. We can try to figure out based on the data which of the 2 models as a whole is more preferred by the data. So LIGO and Virgo, of course, have been playing the game through the black hole route for a long time now. And through that, we have managed to identify around 90 events. And you see them classified here as a function of the total mass. We like to do this kind of classification also for astrophysical reasons. But what I want you to look at, and what I'm going to focus on is guys here on the top, the most massive ones. The ones that I said are difficult to interpret, but quite beneficial if you manage to do so. So why are these so interesting from my point of view? So the main advantage, and this is something that does not really depend on the signal, but on the signal and the detector we're using, is that for this type of events of 100, 150 solar masses, because of the characteristic frequency of the signal at the merger stage, when the strong field is the strongest it can be, then that part of the signal falls in the sweet spot of the detector. That's what the detector sees the best. So that's what gives you the best chance to look for strong field gravity effects, and maybe for violations of GR in that super strong field regime. One way you can see that a lot of information is encoded in that part of the signal is that of higher gravitational wave harmonics. So what are gravitational wave harmonics? A gravitational wave is not only, if you want to call it like that, a single gravitational wave that goes with twice the frequency of the orbit. In reality, black hole mergers are just playing like an orchestra through different emission modes or different instruments. And which instruments you see and which instruments get activated depend on the properties of the source, mass ratios, spins, and so on, and also on where you are around the binary. So the game goes a bit as follows. For any generic binary in general, the quadruple mode, the one we call everyone calls the 2-2, dominates the signal like vastly. But as you get through the merger stage and any asymmetry in the system gets like really exaggerated and encoded in the gravitational wave, this triggers the higher gravitational wave modes. So around merger, you see them for asymmetric black hole mergers. So the more asymmetric the masses are, the more you see these higher harmonics. Now, where you need to be in order to see this. If you are face on, which is where we are with respect to basically all of the LIGO-Virgo events, you only see the quadruple mode. This kind of makes sense that we are only seeing this thing, first of all, because the searches we do look only for this, that's point one. And second, the emission here is way louder. Now, if you move to more equatorial positions where you see, just to say it in some grosso modo way, where you actually see the motion of the two black holes coming and going away from you, you start to see this gravitational wave extra harmonics, and therefore you will get extra information, especially in the merger stage. A way to see that reflected in how the waveform looks is for instance, this. Here on the left, you just see that the old, good, beautiful chirp signal that you see when you are face on to a system. And this is a mass ratio of 3. So you expect that this system is emitting gravitational wave higher modes at some at some orientations. So if you move to the equatorial plane and you start to move around that equatorial plane, after the merger in particular, you don't see any more that end of the chirping signal, you see some more complex structure. And this structure is coming from those extra gravitational wave harmonics. So this is just to visualize or to say in a visual way that there is a lot of information in here that you can gain from observing these high mass systems, and moreover from observing them at equatorial positions. Another effect that you can see when you see the merger is, for instance, gravitational wave recoil. The recoil happens because of the asymmetric emission of gravitational waves. Gravitational waves carry linear momentum, and because at the end of the process, you need to keep linear momentum constant, then the final object, the final black hole, inherits a characteristic velocity that we call gravitational recoil. This is astrophysically really important because these recoils can get to levels of 5,000 kilometers per second, and this is way more than enough to expel the remnant black hole from any possible environment. And that means that this black hole will not merge again with any other black hole, and therefore you will not form this hierarchical black hole merger hierarchical black hole merger formation scenarios. That's a complicated name. And that's important because that's one of the ways that we think that intermediate mass black holes and supermassive black holes can form. Then, if you manage to observe the higher modes or the more than one gravitational wave emission mode during the ring down, then you can test a hypothesis or a theorem of GR that is called the no-hair theorem, the one that tells you that the black hole is characterized fully by mass and spin. What this means is that then any gravitational wave mode that is emitted during the ring down should have its frequency and damping time fixed by the mass and spin. So you can play the game in theory. In practice, it works a bit differently, of detecting one mode, reading the mass and the spin, detecting a second mode, and check whether your inference of the mass and the spin is consistent. And finally, from an astrophysics point of view, because of the masses involved in this type of mergers, you may have merging objects that are between, let's say, 60 and 130 solar masses. This mass range is called the pairing stability supernova gap. And if you detect something in here, the first thing you think is that this black hole cannot form from stellar collapse, because the formation of such black holes from stellar collapse is prevented in principle. So if you see one of these, you would be saying, well, okay, maybe this black hole formed from a previous merger, but then again, that requires very particular characteristics for the environment that is containing that black hole, because that black hole will get kicked and that thing needs to be retained in order to merge again. So where am I going with all of this? High mass mergers are quite important. And I said they are important to me because I want to observe or study the merger and ring down. So the way we interpret these things is via comparing to templates. And when we want to obtain templates or waveforms for this part of the merger, we need numerical relativity. There is no way you do that through analytical techniques or through perturbation theory. You really need full GR in order to do so. You may need GR for other reasons, maybe because you want to compare the data to simulations or to waveforms from sources that are not yet modeled analytically, like highly precessing, highly eccentric sources, exotic compact objects, of course, and even supernovae, post mergers of BNSs, etc., etc. So I don't think I need to convince a group like this that numerical relativity is very important for gravitational wave astronomy. And because it's so important, then we were trying to compare gravitational wave to weird systems. Then we found out, as a lot of you probably know, that extracting the gravitational wave strain that the detectors actually read from an NR simulation is a pain in the ass. And it's a pain in the ass because most of the times, or most of the codes, either export or output, something called the Neumann-Penrose scalar, which for practical purposes is a second time derivative of the strain, or the bond line use. No matter how you put it, you need to integrate, right? And that integration is kind of complicated. Oh, I didn't. Okay. I had a beautiful thing, and I skipped it. Okay, so you need to integrate a time series that is discretely sampled, that is of finite length, and most importantly, it has some numerical noise that you do not have under control. And this is the key point in all of what I'm gonna say. You really don't know what's your numerical noise in that cipher that you wrote with it. So when you integrate, a consequence of that numerical noise getting integrated and integrated and integrated again is that non-linear drift that you end up getting. I seemingly need to press 2 times to advance 1 time. Anyway, okay. So an alternative to that time domain integration is what's called frequency domain integration. So in the frequency domain, integrating in time twice is just dividing by the frequency squared. But what that causes is that numerical noise of low frequencies gets really exaggerated. It gets very increased, and it can really pollute your waveform. So here you have an example of that noise being really exaggerated by the integration. And you may think, well, this may not have a huge impact in the actual waveform. Well, when you picture it in time domain, here is not very strong, but there is an effect. So you need to find ways of easing this error, right? So what people do, or one of the ways they are to kind of battle this error, is what's called the fixed frequency integration. And that consists on choosing a low frequency cutoff, below which you're going to erase basically all frequencies in your waveform. So what's the obvious choice? Basically, if you choose your cutoff too low, so below the minimum frequency of your system, you're going to have a spurious noise polluting your signal. If you, which is what happens if you do this. If you choose it to be too high, then what you're going to do is to kill real signal and therefore sacrificing computer hours just to waste them. So you want to find some optimal place to cut your waveform. And what one usually does is to say, okay, I know that for a circular system, and this is very important, for a circular system, my frequency is a monotonic function of time, and therefore I can kind of choose how many cycles I'm willing to sacrifice in order to protect myself against this spurious noise. So you would usually sacrifice 1 cycle, 1.5 cycles. And this can be done for circular systems just because of the fact that the frequency is a monotonic function of time. Now, first of all, this is an artisan process that involves some trial and error. So there is no unique way to do this. Second caveat, this is easy for circular binaries, but what happens if you have high eccentricity what happens is you have something without any spiral, like a core collapse supernova, or the case we faced, which was a head-on collision that, again, it doesn't have an spiral, so we don't have a natural way of just cutting the signal at some point. The same would hold, for instance, for a dynamical capture, where the frequency is actually evolving in a cycling way because you're doing encounters as a function of time. So what we did is the following. We said, okay, forget about strain, let's try to deal with cipher instead. So usually how gravitational wave data analysis works is the following. You have the detector data that you assume is your GW, which is strain, and your background noise. And the only thing you ever care about in data analysis, the rest are byproducts of this, is the inner product between two time series. In this case, data and template, it could be any two time series. And the ingredients here are the following. Your first time series, which is in this case the data, your second time series, which is the template, and then very importantly, your characterization of the noise, of the detector of the noise, which is in strain. Now, the trick here is if I want to substitute all of this, then how do I deal with the noise of the detector, which is the usual PSD you've seen for sure many times. So the approach we take is the following. If the Neumann-Penrose scalar is just a second derivative of the detector noise, of the gravitational wave, then we can take the detector data and take a second order finite difference. So we get our second derivative. And then in principle, we end up in our cipher version of things, which is just a detector data, which is the second time, let me call it derivative, in where we have the cipher of our gravitational wave and then some background noise that now is cipher version. So the whole thing here is how do we estimate the power spectral density? If we have that, we have everything. And the only thing you need to take into account is that if a process as a function of time is Gaussian, then the second derivative is also Gaussian. So you should be able to transform from one to the other. And then what a student did a student in Hong Kong, PhD student is Isaac Wong, is the following. He found out that you can just, if you get the PSD from LIGO, the power spectral density from LIGO, you can convert that into the power spectral density for cipher analytically via multiplication factor that just looks like this. Key numbers here, for instance, are just the time step of your sampling and the whole length of your waveform. If you compute this and multiply your PSD by this number, then you get the exact, you get the cipher version of the PSD, and you can do your data analysis in a completely equivalent way. So we're saying that we want to go from computing inner products in strain way to computing inner products with cipher. And the two things have to be the same. Otherwise, you're changing the data. So in order to do that, you need to want to check two things. First of all, that when you divide your template by the corresponding noise estimate, you get the same thing. And when you do that, when with the data, you get the same thing. If that works, everything is going to work. So what I'm showing here, just for visual purposes, is in blue, you have the strain extracted from a numerical relativity simulation. This has been obtained by double integration with some type of filtering that was more or less okay. That doesn't really matter. And then in gray, you have the cipher we extracted from the numerical relativity simulation. Okay, so the two are different, of course, and they are scaled so that I can fit them in the same plot. And of course, the two are expected to be different. One is the second derivative of the other. Now, when I whiten, when I divide it by the corresponding noise estimates, in this case, for some chunk of data of LIGO, then you can see that the two things are overlaying. So the two things are exactly the same. So the whitening process is working, and our formalism is going to work. Now, if you want to see the impact of the integration errors for this particular simulation, in which it seems we did pretty well, the second derivative of this strain that carries the systematic errors is in orange. And it differs a bit from the directly extracted from the simulation because of the carriage of the systematic errors. And once we whiten, you can see in there that gray is not exactly equal to the other two. So in this case, the impact of the integration errors was not very large, and we're doing this for nothing. But for other cases where we were not that smart doing our choices of cutoffs and so on, this difference is way large. The second example is here. This is LIGO-Virgo data. So in this case, we took the data divided by the power spectral density of the detector, took the second derivative of the data, divided by the same power spectral density, and you can see that the two results overlay perfectly. The differences between the two are of 1 part in 10 to the 12. So this is the Fourier transform of this, just to see things as function of frequency. You can see that the difference between the two things is about 10 to the minus 12. And the Whiteland data is order 1. So this is 1 part in 10 to the minus 12. So for all practical purposes, this framework is going to work. So now we can use it. How long have I been talking for? So 1905-21. So again, when you compare data to templates, you do the following. You have your data, you have your templates, and you want to extract the posterior distributions on your source parameters. The way you do this is you compare first, let me say it like this, how similar templates are to data, and this is where the likelihood comes. This is just a measure of similarity between the two things. And then once you have the probability of each template given the data, you come with your astrophysical priors and weight them in order to obtain your final results. Astrophysical priors, for instance, can be imposing that the universe has to be isotropic and uniform, and therefore you would favor large distances, which is where it's more probable to find sources. That's an example of what the prior can do. And again, we can play this game for a model of black hole mergers or a model for these rock stars. When you want to do model selection, what you want to do is sort of saying, compute the, let me say it like this, the average likelihood or the average fit of the templates given the data for the whole model. So if you want your model to be preferred, what you need is that templates in your model reproduce the data very well, but that the number of parameters is not too high, because otherwise your model is going to get killed, because the average fit is not going to be good. So that's just a mathematical realization of what's called the Occam's razor, right? So with that, we get to high mass events in LIGO-Virgo. This is 1905-21. You can see this is not a typical LIGO-Virgo event because you don't see here the in-spiral cycles. So what this means is that when you do parameter estimation on this, what you're really looking at is at the final mass and final spin of the black hole that was formed here. And then when you compare it to your templates, including the whole in-spiral merger ring-down process that depend on the masses and the spins of the black holes, what GR is doing for you is the following: is, okay, you give me this final mass and final spin. Now I'm going to tell you all the possible parents that this final mass and final spin can have. And then with your priors, you will subselect from there. So what I want to say is that every time one reports initial masses or whatever pre-merger dynamics here, all of that is very assumption dependent. That doesn't really come from the data. But anyway, if you play the game we played in LIGO-Virgo, and you assume that this is just the end part of a circular in-spiraling processes, then you can infer some properties for the pre-merger dynamics, and of course for the remnant. So regarding the remnant, this was very interesting because you get an intermediate mass black hole as a final object, so a mass above 100 solar masses. But now regarding the pre-merger dynamics, you get two fancy things. The first one is that your primary black hole, or the bigger one, lays within this very instability supernova gap, which is very nice or very interesting, but also challenging. And actually, I haven't seen any analysis involving black hole mergers that points to something different. And you get a mild signature of precession, even though the in-spiral cycles that you have are at most half a cycle. But we know that for systems like this, we showed that precession can be mimicked by eccentricity. So you may be perfectly thinking that something is precessing when in reality, the source of this thing was eccentric. And this is again because you only see a very small part of the pre-merger dynamics whose signal or whose morphology can be imitated or caused by any of these two processes. So because of all of that uncertainty, 1905-21 is consistent with many possibilities. Circular binary and precessing. Precession can be confused with eccentricity, and therefore people showed that this thing can be either eccentric, it could be the end point of a dynamical capture, it could be eccentric and precessing, or what I'm going to discuss now, it could be just not a black hole merger. So that brings me to boson-stars. Again, I'm not an expert in this, so no questions. Sort of saying, no, I'm kidding. So in essence, boson-stars are self-gravitating Bose-Einstein condensates of ultralight boson fields. For data analysis purposes, they are just compact objects that can imitate gravitational wave emission and gravitational effects of black holes. but without having an even horizon or a singularity hidden behind it. And this is very important in our case because of the following. We can simulate mergers of spinning stars, spinning boson-stars, but only head-on in our case. So as far as I know, there is no initial data that is not constrained violating that allows you to perform circular mergers of spinning stars. We need them spinning now because if we do a head-on collision and we want to get the final spin of a circular merger or something that was consistent with a circular merger, which is 1905-21, then we don't have the contribution from the orbital angular momentum to it. So if we don't make the stars spin, then the final spin is not going to be consistent with whatever LIGO-Virgo are seeing. So a solution to that is to spin them, but a lot. We needed spins larger than 1. And this is something that, of course, you cannot do with black holes. We can produce then a highly spinning remnant black hole. A Proca-star merger, well, I haven't yet got to Proca, but a boson-star merger is going to have 2 new physics parameters. The first one, if you attach to a complex case, is the oscillation frequency of the field, which determines the compactness of the star, so how similar to a black hole it is. And the boson mass is going to determine how massive the star can be before collapsing into into a black hole. And that's important because, of course, the signals that LIGO and Virgo are observing correspond to things that form stuff that then forms a black hole. So if we ever want one of those mergers to be a boson-star merger, we need the final star to collapse. Otherwise, things are not going to fit, really. And then regarding cosmology, some people consider ultralight bosons as good candidates to form part of dark matter. The properties of the ultralight boson forming the star or forming the field that's going to form the star are very important to its stability. So if you attach to the scalar paradigm, then you can form non-spinning stars if you neglect self-interactions of the ultralight boson field. But this cannot be spinning. These are unstable against axisymmetric perturbations. Again, if you omit self-interaction. If you want to do a spinning stable star, you need to attach to the complex vector case, and therefore you form something that is called a Proca-star. I think Richard invented those. That's your paper, right? Yeah, we needed to attach to this paradigm. There are ways other than mergers to look for ultralight boson effects in gravitational waves, and people have been carrying those for the case in this case of scalar fields. So fields of ultralight scalar bosons can form another type of astrophysical size object, which is clouds. And its clouds can surround black holes. When they do so, they can trigger a process called superradiant instability. And that's going to do basically 2 things. That's going to produce a continuous gravitational wave emission from the black hole. And this thing has been searched by folks in LIGO and Virgo. And they can also, they will extract angular momentum from the black holes and therefore reduce the spin. So you can find evidence for a population of black holes whose spin is capped at some value, and therefore try to justify that by the presence of these fields. None of those types of analysis have obtained a positive result, but those have been used to place bounds on the possible masses of the ultralight bosons. Now we are doing something different. We're doing mergers. So black hole merger looks like this: in spiral merger, ring down, and then your final black hole. A boson star or a Proca-star merger looks more like a neutron star merger. You get 2 stars, you merge them and form a hypermassive star. And then the fate of this star depends again on the characteristics of the star. If it's not too compact, it may not even collapse. If it's compact enough to collapse, but not too soon, it will survive for a few seconds, depending on the mass, and will emit these characteristic pulses that may well be used as a smoking gun to say these were not black holes, this was actually boson stars. But we're not dealing with this case because what LIGO is being observing is this. So we need to form something really compact that collapses almost immediately, giving us some signal before the merger, and can reproduce what LIGO and Virgo are seeing. So this is the case we're going to be dealing with. So Nico in Valencia performed initially a set of, I think, 90 simulations for equal mass mergers, where he was varying the frequency of the stars that are colliding, but the 2 at the time. So it's an equal mass, equal frequency, equal spin, equal everything merger. And we are including the quadrupole mode, which is the one that dominates for black hole mergers, but also the 2-0, which is co-dominant for head-on collisions. So you really need it if you want to faithfully reproduce the signal. Now that catalog has evolved to a catalog of almost 800 simulations, where we have now unequal masses, which is the same as saying unequal frequencies in the two stars. If you want to know the mass ratios here in terms of mass ratio, things go basically from 1 in the diagonal to, I think, 1.5 or 1.6 here in the corner. And now we can compare this catalog of simulations to LIGO-Virgo data. And so we can play this game. We have LIGO-Virgo data. We have our templates for binary black holes, and we do the typical comparison in terms of strain, because there is no need to get complicated for this. And then we have our ProcaStar catalog. Initially, we did a study using strain, which was okay, not too bad. And then when we realized this problem with integration and that we could ease it, then we started to use the Neumann-Penrose scalar to do this comparison. When we do the comparison with the two models, we can extract two figures of merit. The first one is, of course, the parameter estimates we get from the one side for one model and for the other. And then more important is the evidence for one or the other model, which is what I really care about at the end of the day. Well, of course, if I find something is consistent with a ProcaStar, I want to see the parameters. First of all, I need to see this. So on top of 1905-21, there are two more events, and let me call it one trigger from LIGO and Virgo that could be possibly fit by head-on collisions, because they are very massive and the signal is very short. The first two are these two here, 220 and 1904-26. These are part of the official catalogs of the LIGO and Virgo collaborations. But in terms of the significance, statistical significance of these events in the searches, they're really low. I mean, to be honest, this is something I would never quote as a detection, but people like it. And on the other hand, oh, I'm missing one slide. Okay. On the other hand, there is this guy here that is not part of any official catalog, but this was found by a search that we run in LIGO and Virgo that doesn't compare with templates. It just looks for consistent power between multiple detectors to say there has to be something astrophysical in here. Now, the statistical significance of this thing is really high. It's 1 in 30 years, so it's at least 30 times more than this. And it has not been qualified as a signal yet because it's very complicated. I mean, the black hole merger models that we have really struggled to fit this, to the point that we have mainly 3 models that we use for parameter estimation in LIGO, and no pair of models gives you consistent results, which means at most that the waveform models do not do well to fit this thing. It's not, that doesn't mean this is not astrophysical. So what comes out of the analysis? For visual purposes, these are the 1905-21 data for the 2 LIGO detectors and Virgo. And you see the best fits from the BBH merger, from the black hole merger model, and from the ProcaStar merger simulations. 2 things to take away. The 2 waveforms are pretty similar, so you're not going to distinguish between one model and the other. That's the first thing that comes out. And there are some differences. I mean, in Virgo, you see something. In Hanford, you see something, which lets you know that, well, maybe if this thing was louder, you could conclude something. For the weird event that I was not able to show before, this is how weird it looks. I mean, if you see this as a first detection, no one will believe it. If we now know that we are detecting gravitational waves, then we give it a chance. The 2 models in this case do very differently. So you can guess that the fits to the data are going to be quite different from the 2 models. So you may well prefer one over the other. So I'm not going to dive a lot into the details. These are just the statistical preference for one or the other model given the data. So 1905-21, which is the most significant of the detections, is slightly preferred to be a ProcaStar merger, even though the analyses are sort of intrinsically designed to favor the black hole model. I can develop on that later if you want. The 2 other events with our current catalog of ProcaStar mergers just cannot be fit by the ProcaStar merger, so they are preferred to be black hole mergers. And then the weirdo actually is even better preferred to be a ProcaStar merger than 1905-21. But this is a weird event. It's not yet a official detection, so just for fun, it's there. Now, the most interesting parameter you can extract from your ProcaStar analysis is the boson mass. And 2 things that I want to highlight here, or 3. First of all, for the only event that it's official, and we want, and that is preferred to be a ProcaStar model, we get this mass around 0.85 pico-electron volts, more or less. And the rest of the masses do not come really inconsistent. So that's Then these measurements are not just random, they are informative because this is the prior and this is what we get out of the data. So it's the data that is delivering this type of measurement. You can actually exploit this to try to find joint evidence for a Procastar merger population in the data. And this works as follows. So imagine I have a set of detections and I say, well, maybe I have a subpopulation of something that is different, in this case, Procastar mergers. A way this game is played usually is to say, I have a detection of black hole mergers, and let's see if I find evidence for a subpopulation of eccentric mergers or non-spinning mergers, because that's astrophysically relevant. So you would look at the spins of this. Now, what we look at here is the evidence for one or the other model. With those evidences, we can construct a population model where we consider a fraction of Procastars in it. And then we can perform parameter estimation on this, what's called population analysis, in order to figure out the fraction zeta that would correspond to our set of observations given these individual probabilities. Lots of curves in here. I would say the only really relevant one is this one that you see here, that goes from 0 to 1. It peaks at 0 and it has support all of the way. And this is what we get if we use our astrophysically reasonable priors and we neglect the weird event. So we have something that peaks at 0, makes sense because out of 3 events, only one prefers the Procastar mergers and not that much. And then you have support all of the way to 1. Now, if you try to exploit the mass coincidence and the fact that you have 3 events here that point at the same mass, then you can guess qualitatively, before I show any result, how this would impact. If the 3 events are consistent with a single mass, that means that from my model, I can eliminate 2 masses and just attach to 1. So I'm simplifying the model. That means I'm going to kill it less when I do Bayesian inference. And they should favor it a bit more, not artificially, but because the masses are coincident with respect to a black hole merger model. If you play that game, I'm not going to go through the details, then you can see that that curve that peaks at 0, now it just peaks at 0.4 or so. I'm not saying that 0.4 of the events are Procastars. That's just where the curve is peaking. So, but I think this is an interesting game. It's a proof of concept version of what could be done once we have a larger set of events and we can construct these curves in a more robust way. Just to close, if you give me 3 minutes, I said that I wanted to discuss a bit effects of the wave-like nature of Procastars in the gravitational wave emission and whether we can exploit them to possibly analyze LIGO-Virgo data. So the Proca field is complex. And if it's complex, it means that it's not only characterized by a frequency, but also by a phase. The star is going to be characterized by a phase. If the star is isolated, the phase is pointless. But if the star is going to merge with another star, then the relative phase of merger, then it may have an impact. Because the 2 things are essentially wave-like, you can interpret this as the 2 stars, when they collide, they can be interacting constructively or destructively, and that will change the gravitational wave emission, just to say it conceptually. And actually, that happens. So this is for the case of an equal mass Procastar merger, so equal mass, equal spin, equal frequency, everything. But then we change the phase of merger of one of the 2 stars. And you can see that the gravitational wave emission changes a bit. This is not very spectacular, but this is how it changed. If we attach to an unequal mass Procastar merger, where the 2 stars have different frequencies, then the effect is even more exaggerated. And a way to see this even better is in the frequency domain. So what I'm showing on the left now is just the frequency domain version of this. It's a spectrum of this, where you can see that that change in the phase is not only changing the amplitude of the signal, but also the frequency content. So it's really changing the shape of the waveform. So that means that you should be able to really read the phase from the gravitational waves. And even more, I don't want to call it spectacular, but this is qualitative thing, is the following. When the 2 masses are equal and the 2 spins are equal, so there is left to right symmetry in the system, then you cannot have modes of odd parity, because otherwise you would be having a left to right symmetry. Now, if you have a phase, if you have everything equal, masses, spins, so on and so forth, but you have a different phase, then that should allow you to distinguish between left and right. So you should be triggering these other modes when the 2 stars encounter. And this is what happens actually here. This is the spectrum of an equal mass, equal spin binary. where we are changing the relative phase and we are computing the 3-3 mode. And you can see, well, you don't know where the merger is here, but it happens more or less here. But when the two stars encounter and the phases are different, then this 3-3 mode gets triggered, which would not happen in the case of black holes, because there is no way you put a phase in there. So this is a sort of smoking gun, if you want. So we are working now in a massive catalog where we take that catalog of 800 waveforms and just do copies with different phase differences between the two stars. So we do this game. And then now we are in the process of comparing this catalog to the 4 events I showed to see if there is any preference for any relative phase. And things are quite funny so far, because for 2 of the events, the ones that are one of those that is not very preferred to be a Procastar and the weirdo, you see a preference for a very particular phase. Well, I don't know what to say about it, to be honest. And for the other 2, the thing is perfectly flat. So it seems that this extra phase may allow you to actually not only fit the system better, but also prefer it a bit more statistically. I'm showing here the log-based factors for the non-phase model with respect to the model having the phase. And that's basically it. We are now in the process of finishing this catalog and see what we can say about the LIGO-Virgo events with this extra ingredient in it. So as a summary, we have this, I think, very useful tool to compare numerical relativity simulations to gravitational wave data, and therefore just look for weird stuff. And this weird stuff, I think, is going to appear quite frequently during the 4th run of LIGO-Virgo, because the sensitivity to low frequencies is going to increase a lot. So that means that your masses are going to be higher and higher and higher and higher. And the clarity with which you see the merger and ring down is going to be better and better and better. So you can really play this game of trying to guess whether what you are observing is black holes or something else. Another current application of this thing, it's to study black hole mergers, but in astrophysical environments. So you can perform simulations of black hole mergers in AGNs, in really dense environments, and so on. And these are quite interesting because such mergers can trigger electromagnetic emission. And you can actually read out this electromagnetic emission from the simulations. So you can you can try to do what's called injection studies or simulation studies, where you try to see how the electromagnetic emission allows you or improves your parameter estimation given the gravitational waves. But you have to do it with numerical relativity, so this formalism is nice for that. Other things could be eccentric black hole mergers, etc., etc. So I'll leave it there, and if you have any questions, please shoot.
All right, questions? Well, I think we'll just go first.
We're doing data analysis using your templates. It's imagine that you pick one of your waveforms, inject noise, then try to fit it or to analyze as a binary. How well do you do it?
Not sure if you're saying I inject the Procastar merger in noise and then try to extract with a black hole model.
Yeah, if it's
so you're asking how distinguishable the 2 things are actually. Yeah. So for this case, where I don't have a relative phase between the phases, I mean, for the cases we compare to 1905-21, or for the ones that actually fit, I mean, the expectation is that you cannot distinguish between the 2 models at a reasonable signal loudness, just because otherwise one model will be preferred with respect to the other when I do this type of analysis. We are trying to do basically that, to identify which Procastar mergers can be genuinely tell apart from the black hole mergers. And my guess is that will happen whenever the 2 masses are unequal, which is when you expect to really see this phase difference effect really contributing to the gravitational wave, and therefore giving you something that in principle black hole mergers cannot. Now, the question is, what signal loudness do you need for that? And we are in the process of trying to figure that out. The other thing, I'm just messing around here. The other thing, a qualitatively different thing is this. So I didn't say exactly what this was, but this is the end point of a circular simulation that we don't really trust because the initial data is really not constraint satisfying. But we believe it should look something like this. And if you get these pulses from the transient hypermassive boson-star, then I'm not betting my hand, but that black hole mergers cannot reproduce this in any way. So something like this would really be able to tell apart. Now, the problem is that we are not in a situation where if this is in the LIGO data, we can find it, because the templates that we use in the searches, they are black hole merger templates. So they are going to detect things that look like black hole mergers.
This, but that you can see, I guess, it depends on the scale.
It depends on second, and the total mass. So the small fluidity depends on the frequency of the field. That's correct. And then with the total mass, we either stretch or compress the waveform. I think David.
Can you describe a little bit more what is the configuration of the binaries in the boson-star and the boson-star templates? Like, is everything head on?
Yep. Well, it's not exactly head on. So the simulation starts with 0 tangential momenta. So we just release the stars from rest. Now, because of frame dragging, the trajectory gets a bit curved. So it's not completely head on.
But still, like, if I think astrophysically, then
yeah,
like that just seems wrong. Like,
yeah, astrophysically, it's totally wrong.
So what's the justification then to make that thing that is astrophysically almost certainly wrong, right? Because you know that basically all binaries are going to be, or the vast majority of them, right, are going to be all like quasi-circular, at least when they're widely separated, and they're circularized due to the emission gravitational wave. So why is this a reasonable thing to do?
It's a reasonable thing to do because, first of all, so technically it's the only thing we can do for now. Second, yes, we are using head-on collisions, but what you see, well, so this is 1905-21, by the way. So what you see here is just the merger and bring down, right? So if I can fit this with the end product of a head-on collision, to me, it's very difficult to think that if in the moment I can do circular simulations or less eccentric simulations, I will not be able to find 2 stars that actually go and reproduce this signal as well. So yes, it's astrophysically quite incorrect or quite unlikely to happen. But the fact that I can fit that with that super simple model and it works, what makes me guess is that I should be working very hard on the circular simulations, because surely I will find something that fits.
Now you do quasi-circular simulations, constraint solve for boson-star.
Exactly. Now, the other point, and this is something I did not get to discuss. I don't know if they have some extra slides for that. Probably not. So many facts. No. Anyway, so the thing is about astrophysical priors. So a head-on collision is super weak as compared, especially if it starts from rest and a very short distance, as we do, as compared to a circular merger that has had all the time to accelerate it to black holes and so on. So I didn't say it, but the distance estimate we get under the head-on paradigm is 500 megaparsecs. What you get with circular mergers is 5 gigaparsecs. So it's a factor of 10, right? So that means that your astrophysical prior should favor this thing with 10 squared, because you are more likely to find sources as you go with R squared, right? And even in that situation where my priors are killing by hand, the head-on model is still statistically preferred, because it fits the data reasonably better and it's way simpler. So what that makes me think is that in the moment I can fit this with my circular, or the future circular mergers, the evidence for this model is going to shoot up. And that's going to also be true for the rest of the events I analyze. So this population curve that I showed, and basically the reason I said that I would never say this means I have 0.4 Procastar mergers in my event set is because of what you said. The models are astrophysically relevant. Exactly, but in the moment, the evidence for each individual event is actually, it shoots up because of switching to the circular paradigm. This population curve is going to switch to the right quite a lot. Now, from that to saying that those are Procastars, I think that it's a huge stretch, and in particular, I would need to see some smoking gun, like what I was discussing with them.
More questions?
So, do you think that in the future we'll use this psychoanalysis as sort of a benchmarking?
I would hope so. I don't know the people that do NR here feel about it, but when this was under development, I remember I went to my old group now in Austin. They were in Georgia Tech, and they do NR simulations all the time. they were doing eccentric stuff. I mean, eccentric, but they are eccentric enough, but they were doing eccentric binaries. And they asked me, oh, we would like to convert this to data, but we need to understand the integration because eccentricity is fucked up. And then I said, no, give the waveform to me. And in 2 minutes, we were running parameter estimation without the need for integration. So I think that as far as we managed to make the code public, I would hope that people really use this. Because you avoid systematic, first of all, you avoid the pain of integrating. And second, you know that regardless how small the errors could be, you're free of those errors. So it's a layer you're removing from your analysis. It's an error layer. Sorry.
More questions?
So you had gravitational memory in your.
Yeah.
So I mean,
I tried to skip that fast.
Didn't really show cipher, I guess.
Yes, it does.
How does it?
So I think there is a misconception about memory that is quite. So memory usually, when people show the string waveform, people say, oh, no, the memory is just the permanent displacement you see at the end. Right, but you see that the waveform goes from 0 to something that is finite. So there is a derivative in the middle, right? So that if you take two derivatives, there should be something that related to it. And if you look at the memory in Cipher, it looks like a pulse, which makes sense, right? Because you have something that is 0, then grows in some nonlinear way because it's nonlinear, and then it gets flat again. So you need to accelerate and deaccelerate. So it's just like a pulse. I think I have a notebook where I have it in terms of Cipher. But now, what I would really like to do with this is I mean, you know more about the art than me, but when you do numerical relativity simulations, my understanding is, first of all, if you extract the strain imposing that the final thing has to be 0, then you remove memory by hand. That's one. And if you do not do it, in principle, memory should be there. Or if your resolution of your grid is high enough, I guess. So what I was going with the memory thing is that if that's true, and only if that's true, if there is a way to see the memory in Cipher, then you can compare the memory you're extracting in Cipher with whatever people is plugging at the end of the strain waveforms. So that's why memory is in there. Then there are technical reasons to not to do memory with the strain, because this is super technical. Just because on the right of the signal, you have a signal that is not asymptotically 0. When you do data analysis, you need to send that thing to 0 in order to not to fuck up with the noise and stuff. But if you send that thing to 0, you're introducing artificial power. Now, if you do these things in Cipher, the signal is asymptotically 0 on both the ends, and therefore, again, you don't have that extra power in the signal. You're just dealing with the true physics that is in there. Anyone knows if memory can be extracted from the simulations directly? I'm not looking at anyone. Okay.
More questions? But then I have a few. Yeah, if I may ask, in terms of also on the topic of computational memory and just in general, like the extraction of the signal, I suppose it's performed at finite radii, and how, like, do you then extrapolate to?
That's something that so Nico, the people in Valencia is not extrapolating the signals to infinity, and from our PhD work, I know that that's bad. And it's bad in particular if you're dealing with several modes in the signal. If you only have one, it's not that bad. But if you have, so what I found when I was doing the thesis is that if you combine modes that have not been extracted at null infinity, then you pick the relative phases of the modes, in particular in the ring down wrongly, and that leads to a net waveform that is not the one you would find at infinity. Now we are dealing with signal to noise ratios of 15, so I would not expect that to have a dramatic impact. If we were dealing with a SNR of 100, then I would be really worried. Well, at 100, even the discreteness of the extraction really is a problem.
Also because also I had the naive idea that it was only if you managed to get your signals at infinity, that you would be able to see properly the gravitational-wave memory, but you say that you're saying a finite radius and you're already seeing an effect.
No.
No?
Actually, but at the time, so we're not. When I was talking about the memory, I was not talking about memory extracted from NR. So what I did was I got one of these waveforms that are analytical, that are strained, and then people plug the nonlinear memory using the, I think it's Christodoulou formula or something like that. So you have a waveform with memory. I'm not even assuming that memory is right. But what I can do is to subtract the memory, right? So then I can compute the second derivative of the memory-less waveform and the second derivative of the memory part of the waveform. And then you see how the memory looks in terms of cipher. And it's like a heartbeat.
Okay.
Up, down, go.
Okay. So then, if I may see, unless there's some last minute question, so I can ask a quick one. So, what are the limitations? So, you say that for having something close to a binary instead of something which is mostly head-on, what are the difficulties? If you know how to describe the difficulties you're having in setting up that kind of scenario.
I don't really know the exact difficulties that the NR colleagues are having with that.
Initial data.
It's the initial data. It's the initial data that apparently is not as simple as superposing the two space times and let the system evolve. It's a bit more complicated. Now I know that people, so Katie Clough's group has come with a way to do it.
Yeah, I still the tape thing. Yeah.
I know they can do it now, so hopefully we will start to use it soon. Where we doesn't include me, it's just people in Valencia.
Okay, thank you.
No worries.
All right, so last chance. If not, let's thank us for that.
If you enjoyed the video, like and subscribe.